Well, hello there. Today we're going to work on section 12.2 where we actually get into exponential and logarithmic functions. Alright, right here, exponential logarithmic functions, and our objective today is going to graph. So we're going to get our graph paper handy, or hopefully you have graph paper, and show you how to graph exponential and logarithmic functions. Yesterday I showed you in general what an exponential function is, but to give you a little bit more detail or be more specific, the definition of an exponential function. The definition of an exponential function is a function, and we're going to call this function f of x, such that f of x is equal to a to the x. Now please notice that our variable, our variable is in the exponent. That's why we call it an exponential function. Alright, so we have f of x equals a to the x. A is some positive real number, so a is greater than 0, and a belongs to the element of the real numbers. And it's not 1, so I guess a is going to be greater than 1. Let me change that to greater than 1. Because if a was 1, then it wouldn't be much of a function. So a is greater than 1. That's not the pen I was looking for. Okay, and then that's called an exponential function with a base a. Oh, I thought I changed that. Base, pen. It's harder than it should be. So the a is the base. So base a, f of x equals a to the x. This is our exponent. The variable is an exponent. A is an actual number. It's a real number, and it's got to be larger than 1, and that's called the base of the function. Alright, and what we're going to do is we're going to practice graphing an exponential function. In this one we have our base of 7, so this is y equals 7 to the x power. Let's go ahead and start it off just by the way we would graph most things if we don't know how to graph them, and let's make a table of values. Let's call this x, let's call this y. Let's use -2, -1, 0, 1, and 2. After we graph it, we'll look at the graph and then we'll see if we can identify the domain and the range of this function. So if I plug in -2 for x, I get y equals 7 to the -2, which, if you remember, is the same thing as 1 over 7 squared, which is 1 over 49, which is a really small number, where it comes out to approximately 0.02. I'm going to do the same thing with -1. I'll plug in -1. 7 to the -1 is 1/7, which is about 0.143. I'll plug in 0. 7 to the 0, any number to the 0, is 1. 7 to the first, and then 7 squared. And as we talked about yesterday, exponential growth goes really fast, and so you won't be able to necessarily get every point onto your graph. Just do the best you can. Let's go ahead and plot our ordered pairs. -2, 0.02, well, that's almost 0. -1, 0.14, well, that's really close to 0. 0, 1, by the way, that point will be on all exponential functions because anything to the 0 is 1. And then I have 1, 7, and then 2, 49 is way up there. So I'm going to go ahead and graph this. Now the question is, this x-axis here, I'm never going to be able to plug in a number for x and get it to equal 0. Never. Can't happen. Think about it. 7 to the -100th is still 1 over 7 to the 100th. It's a really small number, but it's never going to be 0. So it gets really close to the axis, but never actually gets there. And so we say that it kind of approaches a limit of 0, and the x-axis is what's known as an asymptote. So in this case, the x-axis is an asymptote, meaning it's a line that our curve will get closer and closer to, but it will never ever touch it or cross it. Now domain is our set of all x coordinates that are on this graph, and our set of x coordinates that we can have on our graph is all real numbers. There's no restrictions on what I can plug in for x. However, there are restrictions on my range. As we just talked about, we're never going to get to 0. So 0, infinity. Notice I have a parenthesis around 0 because it will never get to 0, but it will get really close. So there's the graph of y equals 7 to the x. It has a domain of all real numbers, and it has a range of all positive numbers, and the x-axis is an asymptote. What's the equation for the x-axis if I told you to write the equation? That's right. It's y equals 0. Alright, let's move on to the next problem. That was problem number 1. Okay, now this one's a little bit different. Notice that our base is a fraction that's less than 1. Let's see what happens when we try and graph a function, an exponential function, whose graph is less than 1. Let me close that. Alright, so let's still make a table of values. So I'm going to go ahead and make a table of values. X, Y. Let me go ahead and use -2, -1, 0, 1, and 2. Now let's think about this. Y equals 1/10 to the -2nd. Well, it's a negative exponent, so I'm going to take each and flip it and make it positive. So, oh, I was supposed to flip it. Let's change that. Let's change this. That becomes back to 1. And so I end up with 100. If I plug in a -1, it's 1/10 to the -1, which becomes 10/1 to the +1. 10 to the first is 10. And 1/10 to the 0, 1/10 to the 1, 1/10 to the 2. And so there's our ordered pairs. Let's go ahead and plot them. -2, 100 goes way off the screen, but -1, 10 I can find. 0, 1, once again, is on our graph. 1, 0.1, 2, 0.100. As you can see, it gets really, really small. Will I ever get to the x-axis? No, I will not. So let's go ahead and put that in there. Good. And good. Once again, the domain is going to be all real numbers. It will get to every single x variable one way or the other. It might take a while, but it'll get there. And then the range is all positives, 0, infinity. And then my asymptote is y equals 0 once again. Alright, so far so good? Good. Let's go on to the next problem. That's basically all you have to do to graph exponential functions until we start shifting them left, right, up, or down, following the I hop over philosophy that we studied earlier in the year. And we'll get to that at the end. Alright, logarithmic functions. Logarithmic function is the inverse. A logarithmic function is the inverse of an exponential function. We'll do more work later on as far as converting back and forth between exponential functions and logarithmic functions, because there is a way to convert. But for right now, what I want you to know is that if I give you an equation where y equals log base a of x, I can think about that as x equals a to the y. So again, this over here is read as y equals log base a of x. If I was in second grade and I was asked to do my handwriting, you know, where this is one line, here's the dashed line, and then here's the top line. These are all lowercase letters, y equals log base a of x, and a is a subscript. It's written below, but the log and the x are written on the same line. If I come over here and think about it as well, here is, and if I come back over here and I draw the dashed line, notice that the y is an exponent. That's known as a superscript. So in log form, the a is a base, it's a subscript, and in exponential form, the y is an exponent and it's a superscript. Alright, so that's logarithmic function. We're going to need to get very comfortable with this translation going back and forth. These are equivalent to each other. Alright, so with that being said, let's go ahead and graph a logarithmic function. Here's a basic logarithmic function known as y equals log base 6 of x. So if I want to think about it as based on that translation, I'm going to rewrite this as, well, let me go back and look just to make sure I'm doing it right. Okay, y equals log base 6 of x. Okay, so the y is the exponent. Okay, the a stays as the base. Okay, so 6 to the y equals x. 6 to the y equals x. Now, because this is an inverse function, it's much easier to plug in numbers for y and then solve for x. So let's plug in -2, -1, 0, 1, and 2 for y, and then we'll solve for x. So 6 to the -2 is 1 over 6 to the 2, 1 over 36, and I'm going to guess that that's a really small number. So let's see, I get 0.03, I think, 0.03. Let's see, 1 over 6, that's 0.16 repeating, I'll call it 0.17. And then I have 0, 6 to the 0 is 1, and then 6 to the 1 is 6, and then 6 squared is 36. So now I look at this log function, and keep in mind that logs are inverses of exponents. So remember, our exponential functions look like this. Inverses are reflections over the line y equals x. So our graph should look something like this when we're done. So let's go ahead and plot these points. 0.03 comma -2, really small. 0.17 comma -1, still really small. 1 comma 0 should be on every graph. 6 comma 1, and then 36 comma 2, which is off of our graph here. Alright, and again, I'm never going to get to the y-axis now. I'll never put in a value that gives me 0 for x. So therefore my domain is 0 to infinity, but my range is all real numbers. And yes, we have an asymptote, it's the y-axis, and the equation of the y-axis is x equals 0. So once again, let's kind of recap how we did this. I had y equals log base 6 of x. I know, based on the notes on the previous page, that this is the same thing as this. So if I know this is my equation and I want to graph this equation, I can make a table of values, but instead of choosing numbers for x to plug in and solve for y, I'm plugging numbers in for y and solving for x. Let's try on the next page. Y equals log base 4 of x. Take a minute and see if you can convert this into exponential form, just like we did on the previous problem. Pause me now, do the problem. Okay, welcome back. Here's what I have. I have 4 to the y equals x. Okay, now that you have the correct equation, make a table of values. Put me on pause again, make your table of values, plug in for y, solve for x. See you back here in a couple minutes. Okay, so hopefully you used the standard -2 to 2. When I plug in -2 for y, I get 1 over 16, which is a really small number, 1 over 16. I don't think I have that off the top of my head. But I do know 1 over 4, and I do know 4 to the 0, and I do know 4 to the first, and I do know 4 to the second. I just didn't calculate 1 over 16. I'm going to assume it's really small, -2. And then 0.25, -1, and then 1 comma 0, 4 comma 1, 16 comma 2, which is off the graph. And there's my logarithmic function, y equals log base 4 of x. The domain is only positive numbers. The range is all real numbers again. And the asymptote is once again the y-axis, which is the equation x equals 0. Okay, I hope everything's going well. Let's try this one. Oh my gosh. Alright, so look at this. My exponent has a +1 on it, 2 to the x plus 1. So this is going to be a shift to the left 1. So what I recommend is let's first graph y equals 2 to the x, and then shift left, and then move it left 1. Okay, is this an exponential or a logarithmic function? Notice that we have my variable and the exponent. This is an exponential function. It should have something that looks like this as the shape. Alright, so let's do y equals 2 to the x. Make a table of values, plot the points, graph y equals 2 to the x, and then we're going to go ahead and shift it to the left 1. So when you graph y equals 2 to the x, use a dashed line so that we know it's not our final solution. Take about 4 or 5 minutes, work on it now. Okay, here's what I have as my graphed line curve. It's not very good, but it's the ordered pairs -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4, and then that extends upwards. If I had, I guess I could go 3, 8. That should be on here also. Okay, so I'm running short on time. Here's what the curve looks like, and you can see Alright, there's the answer. Try and do the next problem on your own.